Hello, my name is Annetta Linwood, and today I'll be talking about cellular respiration and how ATP is formed. Okay, so cellular respiration is the process that allows your body to harvest a huge amount of energy from a single glucose. In fact, it is so efficient that you get 30 ATP for every one glucose molecule you eat. So this exercise is going to break down exactly where each ATP comes from. So I'll be talking about glycolysis, the pyruvate dehydrogenase complex, and the citric acid cycle. And I'll also be reading from some handouts and some notes that I have just to kind of make sure that I cover all the information. So kind of forgive me for reading because I want to make sure that I cover all of the information. So let's begin. So glycolysis, it is a metabolic process that serves as the foundation for both aerobic and anaerobic cellular respiration. So it is the first phase of cellular respiration. It has 10 steps where glucose is converted into pyruvate. So I'll just be covering the steps where either ATP is formed or NADH is formed or FADH is formed. So just to kind of help to explain how we get the 30 ATP. So in the first step, one molecule of ATP has been consumed. So this is because glycolysis, the conversion of D-glucose into glucose 6-phosphate, the enzyme is catalyzed by the hexokinase. So basically, the glucose ring is phosphorylated. Phosphorylation is the process of adding one phosphate group to a molecule derived from one ATP. As a result, that one molecule of ATP has been consumed in the first step of glycolysis. Okay, so then we will move down to step 3. So another molecule of ATP is consumed because it provides a phosphate group that is added to phosphate, no fructose, hold on, sorry, phosphofructokinase. So phosphofructokinase with magnesium as a factor changes fructose 6 phosphate into fructose 1,6 bisphosphate. So that's what happens in step 3. Like I said, similar to step 1, the reaction consumes 1 ATP. Okay, so now we go into step 6. NAD is converted into NADH. So we have the glycerol dehy-3-phosphate dehydrates and adds an inorganic phosphate to glyceraldehyde 3-phosphate, producing a 1,3 biphosphate glycerate. Basically, glycerate dehyde 3-phosphate is oxidized by NAD. So NAD molecule is pull a hydrogen off of the GAP, converting it from NAD to NADH. So it is converted from NAD to NADH plus, or NADH in step 6. So then you move on to step 7. So you got the phosphoglycerate kinase transfers a phosphate group from 1,3 bisphosphate glycerate to ATP to form ADP to form ATP and 3-phosphate glycerate. So at this time, we're back to 0 because 1 and 3 consumed ATP, so we're at a negative. Step 6, you get an NADH. You got 2 of those. So then you get to step 7 and you get 2 ATP. So now basically you generated 2, canceling out the first 2, which nets you 0. So now you go to step 10. You got the pyruvate kinase transfers P from PEP to ADP to form pyruvic acid and ATP, which yields 2 ATP. So now you have a net of 2 ATP. So you have 2 ATP, 2 NADH, which yields a total of 5 because you have the 2 ATP. In this instance of glycolysis, you have 1.5 molecules of ATP per NADH. So you get the 2 times 1.5 NADH, which gives you 3, plus 2 NATP, which gives you 5 ATP total. Now that's glycolysis and how ATP is formed in glycolysis. So now we move on to the pyruvate complex, pyruvate dehydrogenase complex. No ATP is formed in this one. So you have NADH. So in step 4, which is catalyzed by E3, the cofactor FAD gets reduced to FADH2 and reverts lipomate back to its oxidized form. So it's back to its oxidized form. Then you have step 5, which is also catalyzed by E3. So you have the hydrogen from the FADH2. It's transferred over to the NADH to generate, NADH plus H plus. Now that just resets the whole complex. So you're only yielding 2 NADH in this instance. So in the pyruvate dehydrogenase complex, you get 2.5 ATP, as shown down here, 2.5 ATP per 1 molecule of NADH. So that's why you have 2.5 ATP times 2 NADH, which yields you a total of 5 ATP in this. So we went from glycolysis, where glucose was converted into pyruvate. Then you go to the pyruvate dehydrogenase complex. So you can't move to the citric acid cycle until you have the pyruvate dehydrogenase complex, because that produces acetyl-CoA, which is the driving fuel for the citric acid cycle. So now you have 5 ATP from glycolysis. You have 5 ATP from the pyruvate dehydrogenase complex. Now we move over to the citric acid cycle. So now you have 10 so far. So lastly, we have the citric acid cycle, which is the second phase of cellular respiration. So in step 3, NADH is reduced to NADH plus H plus H plus. So this is driven by isotrate dehydrogenase. So basically in this step, you have isotrate loses a molecule of CO2 and is oxidized, forming a 5-carbon alpha keto glucotrate. Now, NAD is reduced to NADH plus HD in this process, generating 2 NADH. Now you go to step 4. A molecule of CO2 is removed, and NADH is also reduced to NADH plus H. So, and this is driven by alpha keto glucotrate dehydrogenase. Like I said, the CO2 is lost in this process as well. So step 5, you have GTP is formed, which is a high-yielding molecule and is used to generate ATP when it donates to a phosphate group, ATP down here. So CoA is removed from the soconol CoA molecule and is replaced by the phosphate group. In this process, like ATP, GTP is an energy-yielding molecule and is used to generate ATP when donates a phosphate group, like I stated earlier. So you have step 6. Step 6, succinate is oxidized and fermate is formed, but in that process, the FAD is reduced to FADH2. And this is driven by succinate dehydrogenase. Succinate dehydrogenase. Sorry if I mispronounced it. And lastly, malate is oxidized, forming oxaloacetate. NADH is reduced to NADH and H. So total, you have 6 NADH, 2 FADH, then you have a GTP slash ATP. So in this process, 1 ATP per FADH, 2, you have 2.5 ATP per NADH, yielding a total of 20 ATP because you have 2 ATP. So lastly, here's the breakdown like I said. So in the first stage, you had 2 ATP, and then you had 3 ATP that came from the 2 ATP times 1.5 ATP per molecule, which yielded 5. Then you had the conversion of pyruvate to acetyl-CoA, which is 2, then 2.5 times 2.5, which gave you a 5. And then lastly, like I said, you yielded 20 from that calculation, which gave you a total of 30. So hope I wasn't long-winded. I hope I was able to explain it thoroughly. I'm sorry that my video was long. I just wanted to make sure that I got all of the information in. I thank you for watching, and I look forward to watching everybody else's video. Thank you.